So now let's look at dilation, stretching and compressing. All right, so stretching, graph is going to grow vertically. Compressing, graph is going to shrink vertically. If we multiply a function by a non-zero real number, it has the effect of either stretching or compressing the function because it causes the function value, the y value, to be multiplied by that number. Let's try some functions multiplied by non-zero real numbers to see this. Oh, I'm looking to where to turn the page, and my board, turn the page is now on the top. When a number k is multiplied with the x in f of x, the graph will stretch or shrink horizontally. This is called a dilation. Right? So on the left is the graph y equals x squared. It's real apparent when you notice, when you look at that point, right? Because the scale is the same on both graphs. So you can see it in the shape, but you can also really see it in that point. So 525 is a point on the graph of y equals x squared because 5 squared is 25. Right? So on the right-hand side, we have the graph y equals 2x squared. The 2x is all being squared, so I went and simplified that out, so that made a little bit more sense. So that could be rewritten as y equals 4x squared, because 2 squared is 4. Now notice that same point. So now the y value is 100 instead of 25. We have a vertical stretch by a factor of 4. When a is negative and multiplied by f of x, the function will flip over the x-axis. This is called a reflection. All right, so we have the point 5. So we have y equals 2x squared and y equals negative 2x squared. Notice the y value. So we have the point 550 on the graph on the left. If there's a negative in front of the expression, it's going to make all our values negative. Right? We raise to the power, and now we're multiplying by negative 2. So now instead of 550, we have 5 negative 50. And so since the y values are negative, it's a reflection over the x-axis. So if you have a negative a, the y values become the opposite. That also works the other way. If the y values were negative, they'd become positive. So let's take a look at a few graphs. So here we have 3 graphs. The blue graph in the center is f of x equals the absolute value of x. And then the red graph is 2f of x, so 2 times the absolute value of x. The graph is skinnier. It is stretched vertically, and we could compare a point. Notice we can't compare the vertex. They all have the same vertex because you multiply 0 by any number, it's still 0. But look at the point, there's the point 1, 1 on the blue graph. On the red graph, it's 1, 2. So the graph has a y value that's twice as much as the value of the parent function for y equals 2 absolute value of x. And if we look at the green graph, the graph has a y value that is 4 times the y value of the parent function. So the graph of af of x, where a is any real number greater than 1, is the graph of f of x, but vertically stretched or dilated by a factor of a. Right? So if the coefficient is 2, it's going to be twice as much. Coefficient is 4, it's 4 times as much. Coefficient is 3, the y values are 3 times as much. Here we have a coefficient that is between 0 and 1. The blue graph, the blue graph is y, I don't even know what the black graph is, but the blue graph is y equals the absolute value of x. The red graph is y equals 1/2 absolute value of x. So now all of our y values are half as much. So notice the blue graph has the 0.44 because the absolute value of 4 is 4. The red graph has 4 too, half as much. Right? Because if you take the absolute value of 4 and you multiply by half, you're only going to have half as much. And if you multiply by a fourth, you're only going to have a fourth as much. So the green graph, 1/4 f of x equals 1/4 the absolute value of x. Instead of the 0.44, has the 0.41. So notice that for any x on the graph, the new green graph has a y value that's 1/4 as much as the original blue graph's value. The black graph, I don't remember why I graphed it, is from the other page. This one is, boy, that orientation has been really off, just on the recording. Before I record, it's fine. I go to record, it's not fine. It's not going to be fun graphing. Y equals, this one is y equals 2 times the absolute value of x. Oh, I didn't read that thing. So the graph of f of x, where a is a number between 0 and 1, is the graph of f of x, but vertically compressed or dilated by a factor of a. If the a value is negative, the graph is going to be reflected over the x-axis. So the blue graph is f of x equals the absolute value of x. The red graph is negative f of x, or negative absolute value of x. Notice any x on the new red graph has a y value that is the negative of the original blue graph's value. So instead of 1, 1, we have the point, instead of negative 1, 1, we have the point negative 1, negative 1. If you take the absolute value, it's positive, but then if you multiply by negative, it's going to be negative. So the graph of negative f of x is a reflection about the x-axis of the graph of f of x. The new graph is obtained by flipping or reflecting the function over the x-axis. All right, so important. The following general form outlines the possible transformations. So we have f of x equals a times f. Actually, before we go over this, I had skipped on the last video something you have in your notes because I wanted to wait until we went over dilations, and that is this page right here. Let's go over the rest of this table and then let's go to that page. So I need to move that screen. All right, so if you have a coefficient in front of the function, if it is greater than 1, the function grows farther on the x-axis. Oh, actually, let me look at, yes, farther from the x-axis. So this is what we've been looking at, this one right here. So this is a vertical stretch and compression. And that is mostly what we'll deal with. All right, so if it's greater than 1, you're going to vertically stretch the graph. If it's between 0 and 1, you're going to vertically compress the graph. It's going to be closer to the x-axis. And if c is negative, the function reflects across the x-axis. The second one there we won't be working with as much, and interestingly, you can rewrite, this is a horizontal stretch and compression, and you can rewrite horizontal stretches and compressions as vertical most times. This one, the stretch is along the x-axis. So if it's greater than 1, the graph is going to be actually stretched horizontal, compressed horizontally. And if it's between 0 and 1, it's going to be stretched horizontally. It's actually the opposite of the vertical stretch. But if you think about it, if you're stretching vertically, you're going to be compressed horizontally. So you'd expect those to be opposite. We will really not deal much with the horizontal stretch and compression. So I am not going to spend any time really on that one because we're going to deal with vertical stretch and compressions. You'll see those a lot more. All right, now let's go back to where we were. Oh, I guess I should have scrolled down the page instead of doing it this way. Oh, sorry, got carried away, went too far. All right, so important. Here we have now, let's look at our outline. All right, so the B is not one we're going to be dealing with too much, but we're going to be dealing with the A, the H, and the K. So the A is a vertical stretch by a factor of A. If it's greater than 1. If it's between 0 and 1, it's a vertical compression by a factor of A. And if it's negative, it's a vertical reflection over the x-axis. We would calculate any of those the same way. You would take your y values and you multiply by the value of A. The horizontal compression and stretch is a little different. All right, so it won't be, so horizontal is x, you would multiply by x. But if it's greater than 1, since if it's stretching the graph, it's going to stretch the graph, compress the graph vertically, horizontally. So if B is greater than 1, the graph is compressed horizontally. Okay? That's because you need less of a value to get to the same place. So let me show you with a number. I think that will help. All right, and let's go ahead and you know what? We've been looking at absolute value. Let's just use that one. All right, so no, you know what? Let's use the square root one. All right, so we have y, because this one I can definitely do a compression with. I can illustrate it very nicely. So we have y equals 2x. So that's a coefficient on x, not a coefficient on the whole function. It's inside the radical, not outside. So a vertical dilation, it would be outside the radical. This one is vertical. It's on the whole function. This one is horizontal. It's only on the x. So now, let's think. So if we have the parent graph, y equals the absolute value of x, and I want to get to 4, right? Well, the square root of 16 equals 4. X has to be 16. But what if I have y equals the square root of 2 times x? All right, well, and I want to get to 4 again. Well, this time I only need to plug in 8. Oh man, look at that center of the board. All right, use your imagination here. That's a square root sign. All right, because 2 times 8 would be 16, which is 4. So now x only equals 8. So you see, I don't have a value twice. I don't need a value twice as much. I need a value half as much. So it's going to take half as long to get to the same point because I'm multiplying by 2. So that's why the horizontal compressions and stretches are a little tougher, because when it's greater than 1, it's always the reciprocal. So it's really a compression by a factor of 1 over b. And if it's between 0 and 1, it's a vertical stretch, and you flip it the other way. So if it were 1/2, so instead if I had the absolute value of 1/2 x, that's going to be a horizontal stretch, because if I want to get to 4, now I have to plug in 32. because that would give us, oops, I said 32 and wrote 36. That would give us the square root of 16, which is 4. So this one is a horizontal stretch. And this one is a horizontal compression. So it's the opposite of what it looks like. Like I said, we won't be dealing too much with the vertical and with the horizontal stretches and compressions. You'll see that next year, though. All right, and then H and K, move the graph right and left. Notice the negative's already there, so x minus h is to the right, x plus h is to the left. All right, so remember the sign is the opposite. And then what's added to the end of the function is the vertical shift. If it's positive, the graph moves up. If it's negative, the graph moves down. All right, so let's take a look at this one. Describe the transformation on f of x equals x squared to get the graph of the equation f of x equals negative 2 times x minus 3 squared plus 5. All right, so we have a negative in front. That's a reflection in the x-axis. The 2 is in front of the function. If it was a horizontal, it would be inside the parentheses. Right? Since it's not inside the parentheses, it's a vertical stretch. It's on the whole function. So that's a vertical stretch by a factor of 2. The y values would be twice as much. The minus 3 moves the graph 3 units to the right. The plus 5 translates the graph 5 up. So you should be able to analyze an equation for the transformations that are taking place. All right, so let's take a look at these. We'll write down the parent function, and then we'll write down the translations. The parent function, maybe if I write higher than I think. Oh, I've almost got it. But it's, and then you get to the middle. All right, I'm just going to drag everything. I've had a problem all day with this board on the recording. So it's f of x equals y, x squared, excuse me. I was thinking I was going to replace the f of x with a y. Actually, you know what? Yeah, let's do that. For the parent graph, let's just write y. Y equals x squared. Come on, parent graph. Ah! It broke up my word. We'll fix it. No, move. All right, there we go. I'm going to lock that in place. All right, so translations. Notice we have minus 10. It's not added to x. So this is a vertical translation. This is, the translation is shift, oh, it writes nice here. Shift 10 units down. Only write like that everywhere. The parent function for g of x equals the absolute value of x plus 2 is y equals the absolute value of x. Oh, isn't that a lovely x? There we go. We have a plus 2 added to x. That's a horizontal shift. Remember, the sign's the opposite, so on the horizontal. So if it's a plus, it's really shifting 2 to the left. So shift 2 units left. All right, the next one. So all of these actually are, so translation means we're just shifting. So there are no dilations on this set. H of x equals the square root of x minus 1 plus 6. The parent graph is y equals the absolute, excuse me, the square root of x. Did I say absolute value? Square root of x. You know, if this board would cooperate, I would be finished so much faster. I hope you can read that. All right, and the minus 1 means the graph has shifted 1 unit right. The plus 6 means the graph has shifted 6 units up. All right, let's look at the next one. All right, so the parent function, we have a cube root here, is y equals x, not cube root, excuse me, a cubic function, y equals x cubed. I can write everything but the cube. There we go. All right, so the minus 4 added, so it's with the x, that shifts 4 units right. The minus 5 at the end means the graph shifts 5 units down. I think, let's see, we'll do, this will be the last one. Write a function g of x, that's a translation of the parent graph. All right, so let's go ahead and first we'll draw the parent graph. So the parent graph here is the y equals x squared. So let's see, this one doesn't have a lot of points. I can't use -3. So -2 won't fit. -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. All right, let's go ahead and graph that. Oh, man, I put that in the right spot. I don't know what it is. It's like half the board is just not being cooperative. Oh, first of all, I better lock it. Lock it, please. There we go. And 0, 0. Oh, let's see if I do it right here. Seems like if I move up 2 more than I need to be, I end up in the right spot. 1, 1. And 2, 4. Oh, you know, this point never moved to the right spot when the graph moved. 1, 2, 3, 4. I have no idea how I'm going to connect those points. All right. Make it a little lower. A little lower. All right. If you saw where my pen was relative to these points, you would not know how the heck I am even drawing this. All right. That is terrible looking, but at least it has the points in the right spot. So let's take a look and see how far the graph has moved. All right. It has moved, just go 2 ahead. 1, 2, 3, 4 to the right. Actually, let's just write the point down, because me being able to count, make marks on that x-axis is just impossible. So this is the point 0, 0. So the vertex on the blue graph is 0, 0. And I'll put it anywhere and just move it in position. The vertex on the red graph, so I made the point 2 units higher to get it on the right spot. And that is at 4, 3. All right, so that means the graph has moved 4 units right. And 3 units up. All right, so our model is f of x. All right, there's no stretching here. So if you notice the graph, I think it's easiest to see on the bottom points. It's moving. So if I go from the vertex to the next point, it's 1 to the right and 1 up. If I go from the vertex on the translated graph, it's 1 to the right and 1 up. So it's exactly the same. All right, so our format is going to be A. We're not going to be dealing with B. X minus H. This is y equals x squared, so it's going to be squared, plus K. That's our format. A is 1. Since we moved 4 to the right, that's the H. So, pretty close. And then 3 units up is the K. Good enough. So I'll write this again later, but it's good enough for you to read. So f of x equals, there's no point in putting a 1 there, x minus 3 squared, 4 squared, looking at the wrong number, x minus 4 squared plus 3. Right? So if you just remember the minus is already there, all you have to do is plug in the values. All right, let's look at this next graph. Here is the parent graph. All right, so this is y, it's much better over here. Y equals absolute value of x. So again, I can start with -2. Oh, I could use negative. I have more space on this graph. -4. -4 and absolute value of -4 is 4. I'm not going to use every value. I'm going to use every other. Absolute value of -2 is 2. Absolute value of 0 is 0. And then 2, 2, and 4, 4. Let's just graph those points. So I'm overcompensating like I did on the other graph. I don't have to. It comes in the right spot. Why can't the entire board work like this? I'm nice to the board. I don't write on it in pen. I don't abuse the board. And what does it do to me? All right. So if you notice that our slope is exactly the same. You can see that the graph went 2 to the right and 2 up, and this graph goes 2 to the right and 2 up, if you look at between those points. So again, A is 1. Let's plug in to our equation here. So our format is f of x equals A. This time, since it's absolute value, it's going to be absolute value of x minus h, and then plus k, oops, which went off the screen. And we'll plug in the h and k. All right, so this graph has, so this point here on the parent graph is 0, 0. The same point on the other graph is -4, -1, -4. All right, so the graph has moved, where am I going to write? Actually, let me make this in red. Oops. Did it make it red? Yeah, that way we can match the writing for the transformed graph. I'll write it up here. So the graph moved 1 unit left. So that's the h. And left is minus. And 4 units down. And that's the k. So now let's plug in here. So we have f of x equals, no point plugging in the 1, but this would be x, so So this is h, this is k. This would be x minus a negative 1 minus 4. And then we'll go ahead and simplify. So f of x equals the absolute value of x plus 1 minus 4. And there we go. So I'm going to end this video because it's at 30 minutes and I don't like my videos to be too long. And we'll pick up in the next video transforming these graphs, which we won't be able to write equations for. They're not just a parabola or an absolute value. But we can still take those points and move them about using the same rules as we did on the other two graphs. All right, so thanks for watching and bye for now.